All right, this is part 2 of our topic 1 video for week 3. Jumping right into it, we're going to start by talking about a Wadati-Benioff zone. This is a zone of earthquakes that you find in and near subduction zones that occur in the descending subducting oceanic plate that subduction zones are characterized by. This allows us to trace that upper surface of that subducting plate at depth all the way down into the interior of the Earth. And these are the primary, really the only places where we see deep earthquakes that occur at depths below the lithosphere. Subduction zones are the source of the world's largest earthquakes. And the way that happens is that the overriding plate, usually the continental plate, acts as basically a large spring. So as these two plates are colliding, that spring will get compressed in the upper plate, and then when the stress becomes too great for the friction on the locked interface between the two plates, you get a major earthquake. And that locked interface will release, allowing the accretionary wedge, which exists out here in the ocean, to rise, and that generates a huge tsunami. And that also, at the same time, the subducting plate lurches down in one single movement. Some of the world's largest earthquakes include 1960 in Chile, which was a magnitude 9.5, the largest earthquake ever recorded. Another famous one, Alaska, of 1964, magnitude 9.2. Indonesia, 2004, 9.1, that spawned the famous Indian Ocean tsunami that killed 250,000 people. Japan in 2011, another magnitude 9 earthquake, the fourth largest ever recorded. These are all subduction zone earthquakes. The Cascadia subduction zone, which exists off our shore, is probably capable of generating a magnitude 9 earthquake. Will that occur in our lifetimes? There's no possible way of knowing, unfortunately, but it is capable of producing that size of earthquake, so we must be prepared for that in our future. When you get earthquakes of this size, you are rupturing an entire plate boundary, which extends underground. So in these two maps, we have the rupture areas of famous large earthquakes. On the left, we have a 2010 Chile earthquake, which ruptured magnitude 8.8 and ruptured a large area of the central, the Andean subduction zone. And then the 1960 ruptured an area almost double that size way down in the southern half of Chile. The Great Alaskan Earthquake of 1964 ruptured an enormous area of the Aleutian Trench, which extends along the southern boundary of Alaska and out into the Bering Sea. And when that happened, we had uplift of some coastal areas and subsidence of some other coastal areas further inland. That's because the crust is relaxing. As that spring gets released, the area nearest the trench uplifts, and the area further away from the trench subsides as it relaxes, and that's called subsidence. Here's a computer model of the formation of a new convergent boundary, a new subduction zone. So we start with compression between the oceanic lithosphere and the continental crustal lithosphere, and at this boundary between the two we get the breakage of rock over time. This oceanic lithosphere with compression is heavier, it is more dense, it wants to go underneath the continental crust. So you get breakage, you get very large earthquakes as this plate boundary begins to form, and as that subduction zone begins to activate, some of that continental crust actually gets dragged down into the interior of the Earth with it. In this area we call the mantle wedge between that subducting plate and the overlying continental plate. So this is the basic process of how that occurs. That it takes several million years. This computer model ran for a simulated 3.2 million years to generate this subduction zone. And this process creates our oceanic trench offshore and our volcanic arc onshore. So to recap, our subduction zone has 4 major components. A deep ocean trench where at the boundary between the oceanic lithosphere and the continental lithosphere. An accretionary wedge where those oceanic sediments get scraped off by the overlying continental plate into a large pile. This big pile parallels the trench, and you get lots of folds, thrusts, faulting, and earthquakes in this zone. Next, you have a forearc basin, which is the area where continental sediments coming off of your continent get deposited in a slightly depressed area between the accretionary wedge and your continent. And then on the continent, you have that volcanic arc where melting induced by water coming out of the oceanic lithosphere causes melting of the mantle wedge, driving volcanism, magmatism, and the creation of your volcanic arc on the mountain range on shore of your subduction zone. And below that, we have here a schematic of our Pacific Northwest, where the Juan de Fuca plate goes underneath the North American plate, creating our accretionary wedge, of which the coast ranges apart, the Willamette Valley, which is part of our forearc basin, and our Cascade volcanoes, which is our magmatic arc. You'll notice that our volcanoes are not at the plate boundary. There's a gap between the ocean trench and the volcanic arc. That's because the subducting lithosphere has to reach a certain depth where the flux melting is most likely to occur, and that's from about 100 to 150 kilometers deep. So the subducting plate has to descend a ways before that melting begins, which drives your magmatism and the creation of your volcanoes. This distance between your volcanic arc and your ocean trench is called the arc-trench gap, and it reflects the depth at which your subducting plate gets deep enough to cause that melting. Down below, you can see a schematic of a few different subduction zones in the West Pacific, where we have, these are earthquakes along, reflecting the depth they're occurring and the distance from the plate boundary, the actual trench. Here in the Philippines, you have a relatively gentle sort of curve where these earthquakes are occurring. That's your Wadati-Benioff zone. The Marianas subduction zone, the plate is descending really steeply, so we have a very sharp Wadati-Benioff zone, very steep. So this means you're going to have a very short arc-to-trench gap, whereas in the Philippines, you're going to have a very long arch-to-trench gap. You can see in Java, another very long arch-to-trench gap. And then in Japan, you have the longest of all, the shallowest Wadati-Benioff zone, which takes place over the longest distance. Here in the Pacific Northwest, our arc-to-trench gap ranges from about 150 miles wide at Crater Lake to about 200 miles to about 250 miles up in northern Washington. At Mount Rainier, it's about 200 miles. And remember, when you get this on land, it's called a volcanic arc. And when you get this in the ocean, such as Japan or the Philippines or Indonesia, you get an island arc because those volcanoes form islands out in the ocean. Another recap, our new ocean floor is getting created at a divergent plate boundary. Initially, this is bare rock, just lava, basaltic lava that has freshly erupted on the seafloor. And as time occurs, as your oceanic crust moves further away from that spreading center, the mid-ocean ridge, it gets covered in ocean sediments. In many places, this is just dead ocean matter, dead plankton. As you get closer to the continent, you will get terrestrial sediment, sand, silt, mixing in with those dead ocean creatures that builds up a thick layer of oceanic sediment. And remember, that gets scraped off into the accretionary wedge, or a prism, as your subducting plate subducts and reaches the overlying plate. This accretionary prism is made up of a bunch of different stuff. Most of it is going to be oceanic sediment, including sand, mud, maybe some volcanic ash, as well as dead ocean creatures, which is a sediment called ooze. But you will also get the upper parts of your oceanic plate, which is going to be mostly pillow basalt and some sediment. So you will get pillow basalt and other oceanic volcanic rocks mixed in with the sediments in your accretionary wedge. And then after a significant amount of time goes by, subduction ultimately ceases when two continents collide, and your detached oceanic lithosphere will break off of your continental plate and sink on its own down into the Earth's interior. And as you get your continents colliding, you get a collisional mountain belt. With some magma chambers will form in here, some melting just as you increase pressure on your crustal rocks, and we call those sutures. Suturing magmatic bodies. An interesting thing that occurs rather rarely, but it does still occur, is the process where some of your oceanic lithosphere will actually override your continental lithosphere, go up on top rather than down below. So ultimately, as your continents collide and your subduction ceases, the accretionary wedge and segments of your oceanic lithosphere will get caught up in what we call the suture zone, where your two continents are meeting and sort of merging into one. The contact between the two continents, in other words. This results in the exposure of something called an ophiolite, which is a sequence of rocks representing your oceanic lithosphere that is now part of a continent. The process where a small piece of oceanic plate goes over or on top of your adjacent continental plate rather than going underneath is called abduction. Remember that. Abduction is the process by which your ophiolite is attached to the continent on the top of the continent. The opposite of this is called underplating, where a small segment of oceanic crust will get accreted to the bottom of your continental plate rather than descending with the rest of the plate. So remember, abduction, your oceanic crust is going over your continental plate, and then underplating, your oceanic crust is going under your continental plate and becoming accreted or attached to the continental crust. Take a second here to look at these diagrams to really understand how your ophiolite ends up on top of the continent and what it's really made of. At the top of your ophiolite sequence are going to be marine sediments. These are deep ocean sediments as well as terrigenous silts and sandstones that come from your continental plate. Below that you have the pillow basalt, the actual eruptive rocks from your mid-ocean ridge spreading center. Below that you have something called sheeted dikes, which are vertically overlapping intrusions of basalt that formed from your divergent plate boundary. These are dikes that have formed over and over and over again and intruded each other and formed parallel vertical series of intrusive basaltic rocks. Then below that you have the magma chambers, which have solidified into a rock called gabbro, which is your intrusive version of basalt. So to recap, marine sediments, then pillow basalt, then your sheeted dikes, which are kind of complicated, then below that your intrusive basaltic rocks called gabbro. And all of that on top of your uppermost mantle rock, which is called peridotite. So your ophiolite sequence, which is the whole thing, consists of your entire section of oceanic crust and a small sliver of the uppermost part of the mantle rock. This is all lithosphere. It's just separated into crust and mantle by its composition. We have several ophiolite sequences here in the Pacific Northwest, in Oregon and Washington, but the best one in the world is located in Oman, where a huge section of ophiolite is exposed at the surface, where we have a huge section of oceanic lithosphere having overridden the Arabian plate. And it actually incorporates the moho, which is the compositional boundary between your ocean crust and your uppermost part of the mantle. Remember, this is all lithosphere. It's just separated into crust and mantle by that moho, the transition zone between layered gabbros and peridotite, which is an intrusive ultramafic rock. Here's what pillow basalts look like in outcrop in Oman. You can see these overlapping lobes. If you watched the underwater footage from Kilauea, you will have seen these lobes forming in real time. And in outcrop, they look like these overlapping, sort of intertwined, weird-looking lobes. This is your pillow basalt. Then you have your sheeted dikes, which are these vertical igneous intrusions which are stacked up next to each other. This is also in Oman. Person for scale. And then you can see the layers in this outcrop, and this is the layered gabbro. The next image is a little bit clearer, where you can see these layers of intrusive basaltic composition gabbro intermixed with peridotite. So that tells us you're getting really close to that moho discontinuity, where your peridotite and your gabbro are mixing together. So these are very closely spaced gabbro intrusions in the uppermost section of your peridotite mantle rock. Now remember from a couple lectures ago I mentioned accreted terrains. These happen when something is stuck on your oceanic lithosphere and then it gets accreted or smeared onto your continental plate during subduction. And these are called terrains. Smaller pieces of buoyant crust that are formerly part of your oceanic plate that get scraped off and accreted onto your continental plate. The entire western portion of North America is composed of these accreted terrains. A better definition of a terrain is a piece of crust surrounded on all sides by faults that is noticeably different from adjacent pieces of crust. Notice the spelling on terrain, T-E-R-R-A-N-E rather than A-I-N. Terrains can include pieces of continental crust that have been moved along faults. It can include island arcs, like Hawaiian Islands or Indonesia is a good example, that have been smeared and scraped off and accreted North America. It also includes seamounts or microcontinents or pieces of uplifted seafloor. These are all things that can be parts of accreted terrains. Terrains get accreted onto something called a craton. The craton is the oldest area of continental crust that has been relatively stable for at least the last 1 billion years. And by stable, that means not involved in mountain building or other faulting or geological deformation. An area where the craton is covered with sedimentary rocks is called the platform. And the part of your craton that is not covered with sedimentary rocks is called a shield. Look at this cross-section down here. You have your basement rock, which is part of the craton, either covered with younger sedimentary rocks, where it's the platform, or it's exposed and uplifted at the surface, which is called the shield. In North America, the shield is called the Canadian Shield, and it composes the northern portion of Canada, part of Greenland, and it is surrounded by a platform which composes about half of Western Canada and most of the United States Midwest. And it is surrounded on all sides by orogenic belts, which are mountain building belts. We have multiple orogenies, or mountain building belts, here in North America. In the West, we have American Cordillera. This is called C-O-R-D-I-L-L-A, Cordillera, the orogenic belt. And then we have the Appalachian orogenic belt on the east coast. And again, these orogenic belts surround the platform, which surrounds the Canadian Shield. The process of continent-to-continent collision is called orogeny, O-R-O-G-E-N-Y, and we have a huge belt of these currently forming in the world, the best example of which extends from the Himalaya in Asia all the way west to incorporate the Alps, the Pyrenees between Spain and France, and the Atlas Mountains in Morocco. This is all part of the Alps-Himalayan orogenic belt, where the African and Indian and Arabian plates are moving northward into the Eurasian plate and building up huge belts of mountains in between the two plates. During these continental collision and orogeny events, we get the thickening of the crust, which increases the pressure and temperature of your crustal rocks, which leads to large areas of regional metamorphism. Metamorphism is the process by which one rock changes into another kind of rock after being subjected to heat and or pressure. So if we look up above here at this cross-section of an orogenic belt of a mountain range, we have our rocks increasing in temperature and pressure underneath the tallest part of your mountains, which is your mountain root. And that progression goes from shale, which is basically a sedimentary rock, to slate, a low-grade metamorphic rock, a medium-grade metamorphic rock called phyllite, a high-grade metamorphic rock called schist, and a higher-grade metamorphic rock called gneiss. Over here in the lower right, you can see the different zones of metamorphism that occur and the different names for these zones of metamorphism. And remember, isostasy of your tall mountains is part of this whole process. The isostasy causes your new mountains to flex your continental lithosphere and sink down into the asthenosphere. Erosion acting on those tall mountains removes material and deposits sediments off on either side of your mountain range. Then your isostatic process is uplifting those mountains and keeping them tall for a long period of time. After an even longer period of time, your asthenosphere has almost returned to its original position, and your mountains are almost completely eroded away, returning almost to your original continental thickness. The Appalachian Mountains of the eastern United States are almost at this last stage down below, and your Himalayas are at this first stage up above. Here's those examples again. The Himalayas, very, very tall, the tallest mountains in the world, with a very thick crustal root. Some of your crust is 80 to 100 kilometers thick in the Himalayas. After a little while, you have some crustal rebound, so you still have high, tall mountains, but are not nearly as tall as they were before, and they are being dominated by erosion. An example of these is the Brooks Range in Alaska, which contains Gates of the Arctic National Park, which is where this picture is from here in the middle. And then in eastern North America, the Appalachian province has almost completely returned to original crustal thickness. We have very little rebound, we have a very small crustal root, and we have very low-lying mountains. The highest part of the Appalachian Mountains only being a little over 6,000 feet above sea level. And remember, this is all part of the Wilson cycle, the process of continents splitting apart and forming oceans, and then those oceans collapsing down and forming mountain-building zones and colliding those continents and building up supercontinents like Pangaea, which then will eventually break up and create spread-apart continents like we have today. These are all part of the Wilson cycle. Thank you. This has been Topic 1. Be sure to stay tuned for the Topic 2 videos.